Okay, so the natural question to ask now is, how do we build symmetries into the laws of nature, or equivalently, into the equations of motion? So how do we build symmetries into the equations of motion? You might tell me you think that nature is Lorentz invariant. Well, how do I build Lorentz invariant equations of motion? Well, what I would need to make sure, I need to make sure that the Lorentz transformations will map solutions to the equations of motion into solutions to the equations of motion. But how do I do that? Well, if my action is unchanged by a symmetry, then if I transform the solution, I'll have the same value for the transformed solution. So imagine that the action S is invariant under the symmetry. Then, if you have a minimum of S, so you've got some function which is a minimum of f of S, then after the transformation, you still have a minimum. So it's pretty obvious that if the action is invariant under the transformation, if I take some function and I transform it by the symmetry and I plug it back into the action, I'll get the same value. So I'll take a minimum of the action under the symmetry transformation into another minimum of the action. But the equations of motion, or the solution to the equation of motion, is the minimum of the action. So this statement over here is the statement that we will take a solution to the equations of motion into another solution of the equations of motion by performing the symmetry. So, to build a symmetry into the laws of nature, let me say equations of motion, to build a symmetry into the laws of nature, the equations of motion, what you should do is build an action S that is invariant under the symmetry and get the equations of motion by requiring delta S is equal to 0. Because the action is invariant under the symmetry, you're guaranteed to map a minimum of the action into a minimum of the action, but that means you're guaranteed to map a solution to the equations of motion into another solution to the equations of motion. Okay, and that gives us now Lagrangian mechanics. So what were the key features? Let's just summarize a little bit. So the key features of Lagrangian mechanics is that, determinism is certainly not manifest. We specify an initial condition and a final condition, and then we find the classical path, or it would be a classical field maybe, that is consistent with the initial and final conditions, and that minimizes the action. And when we did that, we found exactly Newton's second law. So determinism is not manifest. We have to specify something now and something in the future. We've just obtained Newton's second law. So what did we gain? Why is this useful? Well, what the action allows us to do, it allows us to build equations of motion that have a specific symmetry. So here is the very important conclusion. To build a symmetry into the equations of motion, build an action that is invariant under that symmetry. And get the equation of motion by requiring delta S is equal to 0. Because the action is invariant under the symmetry, a minimum of the action will be mapped into a minimum of the action. And because we get our equations of motion by saying delta S is equal to 0, our solution to the equations of motion is the statement that we're at a minimum of the action. So the advantage of the Euler-Lagrange formulation of mechanics is that it gives us a very simple way to discuss symmetries. Good. Now, one last question I'd like to consider before we leave Lagrangian mechanics, and that is, so I want to really ask, how general is the Lagrangian formulation of quantum mechanics? So, is there a Lagrangian for any of Newton's laws? So, you know, there are many different laws that we could write for Newton too. Can every single one of those be obtained from a Lagrangian? And in fact, the answer is no. Newton's laws are more general than Lagrangian mechanics. And the place where Lagrangian mechanics fails is when you're describing problems that might involve things like friction and dissipation. And I want to give you an example so that you can really see that what I'm telling you is true. So I want to consider a problem with friction. So the mass times the acceleration of the particle, I need to write down a force. So friction always acts to oppose the motion. So let me put down a minus over here. And then the frictional force is always velocity dependent. So let me write down dx dt. This is what you would get for friction at very slow speeds. For air friction, when you're moving a bit faster, the friction might be proportional to the velocity squared. But anyway, this is the law that we're going to take. And this is an example of friction. It's a force whose size depends on how fast you're going, depends on the velocity, and it acts in opposite to the direction of motion, which is what that minus sign is telling you. And I claim you can't get a Lagrangian that gives this equation of motion. Now, remember the Euler-Lagrange equations? D by dt of dl dx dot is equal to dl dx. Let's try to invent a nice Lagrangian. Well, for this term over here, it's obvious what I should do. So L is equal to 1/2 m dx dt squared. Okay, I know that this term in the Lagrangian is going to give me the correct left-hand side for Newton's laws. Now, what about this term over here, the friction term? Well, I'm going to make a guess. This is what I'm going to guess. I'm going to say minus x dx dt. The reason why that seems like it's a good guess to me is that when I take the L dx of this term, remember I should ignore the x dots, so I'll just get minus dx dt, which is the correct right-hand side. So that's my guess for the Lagrangian. Okay, let's check it. Let's see if this guess is okay or not. So first of all, we need to calculate the L dx dot. Well, the L dx dot from the first term, this is just mx dot, m dx dt. So you've seen this, we've done this quite a few times. And then minus, then the L dx dot, well, in the second term of the Lagrangian, there's an x dot. So if I ignore the x and just differentiate back to the x dot, I'll just get a minus x. So that's the one thing that I'll need. The other thing that I need for the Euler-Lagrange equations is what is the L dx? Well, there's no x's appearing in the first term of the Lagrangian, so forget that. In the second term, I ignore the x dot. If I calculate d by dx, I'll just get minus dx dt. So now what does the Euler-Lagrange equation say? Well, I will have d by dt of dl dx dot, that's m dx dt minus x, and this should be equal to dl dx, which is minus dx dt. So if I work out what this is, taking a derivative of the first term, I'll get m d2x dt2 minus dx dt is equal to minus dx dt. Well, the two dx dt's cancel, so I land up getting m d2x dt2 is just equal to naught. So this is the equation of motion for a free particle. So I failed. I didn't manage to get the force law that I wanted. I didn't manage to get that force law at the top of the page. And I claim that whatever Lagrangian you try, you'll never get that force law at the top of the page. But notice there's something a little bit interesting about this answer. So from this Lagrangian over here, so I'm going to outline it in green. From that Lagrangian over there, I got the free equation of motion. So exactly the same equation of motion that I would have gotten from this Lagrangian. These two Lagrangians give me exactly the same equation of motion. So it means the second term that's added to this first Lagrangian actually doesn't contribute. Well, why not? That's a bit strange, okay? Why doesn't that second term contribute? I want you to think about that and see if you can come up with a good explanation. And if you get a nice explanation for this, it shouldn't involve applying the Euler-Lagrange equations. You should just be able to look at the action and see why does the second term not affect where the minimum of the action lies. So think about that. That's a nice problem for you to try and solve. This now completes our discussion of Lagrangian mechanics. We're now going to move on to Hamiltonian dynamics.